right. Hopefully everything is now recording. Okay. So this is the fourth tutorial as part of this 3D simulation tutorial sessions. Previously, we had a couple of tutorials by the Bahia RT team for just basic ramping up on how to run the 3D simulator, and also, for instance, running in containers. And furthermore, or after that, the Magma Offenberg team gave a tutorial on their very recently released codebase in Java. And today I'm going to be talking about the UT Austin Villa codebase release, which has been out for, I think, since maybe 2016 or so. One difference between the UT Austin Villa code base versus the Magma Offenberg team's code base is that the Magma Offenberg team's code base is in Java and the UT Austin Villa code base is in C++. So if you have a strong preference for one programming language over the other, that could be a good reason why you might want to choose one or the other as a starting point for your team. Now, I'll also mention that I'm not going to go into a lot of details of just generally how to run the 3D simulator and the monitor Roboviz and things like that, because that was previously covered in the Bahia RT teams tutorials, which you can check out the links here on YouTube. I believe it's on their Bahia RT YouTube channel to check that out. Okay, so just a little bit about the UT Austin Villa team. I think the first year that the UT Austin Villa team actually competed in the 3D Simulation League was back in maybe around 2007 or 8. I forgot exactly which. And the team has also competed pretty much every year in the standard platform league. So using the physical now robots instead of, which is the physical robots of the humanoid robots that we're using in the 3D Simulation League. Now, the UT Austin Villa team has done quite well over the past roughly 8 or 9 years. I believe we've actually won the competition 8 out of the past 9 years, if I'm counting that correctly. And as well as the year that we didn't win, I believe we got second in the competition. So the team has been doing quite well with our code base. And so back in, I think, once again, maybe 2016 or so, we decided to release a base code of our code base so that other teams might be able to use it to quickly ramp up in the league, and especially for new teams to join the league. So that's what I'm going to be covering today and talking about. Now you can find our code base on GitHub, just if you search for UT Austin Villa 3D. And I'm going to now quickly go through and show you what you need to do to actually run the code base. So first, let me just make sure I don't already have the code base installed. I'm going to do a fresh install of the code base and build and show you a few things about that. So what you first want to do is clone it from GitHub. So that's pretty easy. You just do git clone and the link that you can pull off GitHub. Okay, so once you have cloned it, you can then just cd into the base directory. And at that point, and there are instructions for doing this on the main page here of the repo. We want to type cmake to configure things correctly. Now, this is purposely going to fail here, as I'll show you in a second, and I'll explain why. And this is just to show you a potential pitfall that you might run into. So one of the things about our code base is that it requires that you have already installed RCSS Server 3D, the soccer simulator. And if you haven't installed it, or if you've installed it in a purposely built and install it in a location that is not like a default, such as /user/local, then our binary won't be able to find the necessary include files, and so it will fail, as you see right here, when we run CMake. Now, in this case, I'm purposely doing this on this remote machine here where I have installed the server in a custom location just to show you how to deal with that. If that is the case, what you'll want to do is set your SparkDir environmental variable to the location which you've installed the server, which I'm doing right now. And then if you run CMake, it should be able to find the necessary include files such that it can actually configure uh, the code base. And then once we've done that, we can just simply run make, which I'll do right now. You can use the J command to run it in parallel for the compilation. And we see I quickly compile here. It shouldn't take very long. And I think we should be good to go. Great. All right. So I'll also mention that our code base is supported on at least both Ubuntu 18 as well as Ubuntu 20. This remote machine here I just compiled on is running Ubuntu 18. I'm now switched to my local machine to run stuff, which is running on Ubuntu 20. Now I'm just going to redo the same configuration here. Which I've already pulled down from Git. I run CMake again. I'm going to recompile it. Actually, I already had it compiled, so first clean it and then recompile it. This shouldn't take very long. Great. All right, so now that we've built the code base, we're pretty much ready to try running it and see what happens. So first, we need to start the server. RCS is server 3D. And we're also going to start Roboviz, the monitor. So this pulls up a field for us. And now we can simply, to start the agent team, you can run just simply start.sh. You can also give it a host name, such as localhost, which is the name of the host that the server is running on. If you don't provide that, it will just default to localhost. Let's try running this and see that we have a team here starting to load up. Okay, so this is just going to when you first build the code base, it's going to provide just sort of I think a little bit of an interesting default behavior. So I'm going to start the yes. Oh, sorry. Oh, if anyone has questions, feel free to type in the chat or even just interrupt on the audio if you so choose, just in case I don't see something pop up in the chat. All right, so just going to start this running. And what you'll see here is this sort of a demo behavior where the robot that is closest to the ball, this one right here, oops, is going to go to the ball and try and kick it into the sort of circle that all the other robots are kind of slowly walking around and wandering around. And each robot, whenever it's the closest to the ball, is just going to try and kick it generally towards the center of the circle. And they sort of just keep circling around in this formation pattern. This is just kind of a little quick, interesting demo here of showing some of the things you can do in the code base. And I'll jump into a little bit more shortly of some of the kind of primitives for control and things like that we provide. But this is, just a simple beginning kind of demo behavior here. I'm going to go ahead and just shut this down for now. So I want to quickly kind of go over what's included in the code base and then kind of allude to what I'll be really kind of diving in today on, as well as a few things that are not included. So what is included in the code base, make this a little bit bigger, is an omnidirectional walk engine, which is based on a double inverted pendulum model. This is actually something that we had originally um, created and designed on the physical now robot and then ported it over to the 3D simulator. There's also a skill description language for specifying parameter skills and behaviors. These are things like kicking a ball or um, maybe even like a goalie diving behavior. And I'll talk a little bit more about that in a bit. We have get up behaviors. When your robot falls over, you need to be able to, get up again. We do provide in this code base some basic kicking skills. We just saw this sample, or actually, we also provide some demo behaviors for just dribbling and kicking a ball towards the goal. There's a whole world model which keeps track of everything that's all the positions of the different objects in the world, such as the ball, where you are, where your teammates are, where the opponents are, and it uses a particle filter for localization. Additionally, we provide a Kalman filter for tracking objects. Basically, we mainly use that for just tracking the ball right now. Of course, we have all necessary parsing code for sending and receiving messages from and to the server. Also briefly mention or show a demo in a bit of code for drawing objects in the Roboviz monitor. That's typically used for debugging purposes. We also provide a communication system, which I'll also dive into a little bit more, that allows you to communicate with your teammates over sort of a limited bandwidth channel. You can say things like where the ball is, or maybe what you're doing, or where you currently are in the field. Um, Another important aspect of our code base is being able to, well, we provide you with a basic kick and walk behavior to be able to actually optimize or learn different kicks and walks. So I'll take a little bit deeper dive on how some of that works. We do have a support for uh, a RoboCup 3D simulation plugin in Gazebo. I'm not planning to dive into that today, but that's something else we support. And there's briefly mentioned some scripts for collecting lots of game statistics, which some people might find useful. And then also something I just added yesterday, which I'm hoping to get to and talk a little bit about, is support for running with this new fat proxy, which is planning to be a part of the league as sort of a challenge or side competition this year for 2021. And I'll talk a little bit more about that when we get to that. Now, some things that are not included is we don't want to just completely release our full code base such that someone could type make and have something that is super competitive out of the box. We want people to kind of work on developing their own teams and strategies and formations and things like that. So we don't provide all of our skills, such as like our long kicks and goalie dives, as well as some of our fastest learned walks. But once again, we do provide mechanisms that you can use to actually learn longer kicks and faster walks and things like that. And then something else is we don't provide our complete high level strategy for things like formations and role assignment and such. This is actually something though that I'm planning to maybe even as early as today, and I'll talk a little bit about this and show a demo of it. I have just recently added locally, but haven't pushed it yet, a simple example for formations and even a greedy dynamic role assignment so that you can have something that it can play not great soccer, but something right out of the box, just as an example of that. So yeah, let me move on from here and give you now a little bit of a high level of the code base and what's really kind of going on at a very high level 10,000 foot view. Basically, in the code base, we have our high level strategy at the very top of this diagram, and the strategy uh, needs to work with a world model to kind of know what's going on, and at every simulation cycle, the high level behavior uh, gets observations of the world, and then needs to decide some what we call skill or kind of high level action to take. And this can be such as walking or turning in place. It can be kicking the ball, or if we've detected that we've fallen over, we might execute a behavior to try and get back up off the ground. And if you're a goalie, even it could be a behavior where you're diving or something like that. And when we've decided what skill that we want our robot to execute, I'll talk a little bit how we define those later in a bit. Then we will have particular joint angles, which are either just directly specified or perhaps computed through inverse kinematics that we want our robot to assume. And then we use some underlying PID controllers to uh, actually compute the specific torques on our joints such that we can achieve those target joint angle positions. So it's a very high level view, and I'll later kind of dive into kind of how the code is organized and what's going on there. First, though, I would like to just kind of tell you if you're just starting out, really the most basic thing, a lot of this you can be abstracted away and just operate in this high level behavior strategy area. And I'm going to show you pretty much just the one or two functions that you need to worry about and deal with to actually create your own team, and just focus on, say, high level strategy. So that is this is VS Code here for our code base. That mainly a file you could just almost solely focus on just out of the box with our code release is a file called strategy.cc. So I'll pull that up. And there are really two main functions that you need to worry about in this file. The first is the beam function of now behavior, or beam method. And what this does is it's called whenever you need to beam or kind of teleport onto the field, say at the beginning of a game or before a kickoff after a goal has been scored. And it just gives an X, Y, and angle position that for any particular agent that you want to assume. And the other main function that one needs to worry about is select skill. And as I mentioned, that we have these skills such as being able to walk or kick a ball, maybe even dive if you're a goalie. Uh, Select skill as part of now behavior just basically decides what are you going to do now? What, given the current state of the world, which you can get from this world model object that's part of now behavior, what do I want to do? And we give a number of different commented out here demo behaviors that you can use, or as well as examples of how to access information in the world. For instance, if you want to know what your current uniform number is, so you know maybe that if you're number one, for instance, you're the goalie, or things like that, you can just query the world model with get unum. We also, the world model will tell you your current position on the field in global coordinates. You can just call the get my position. You can get your angle as well, your orientation in the world. So that's and also you can get where the ball is by just calling get ball on the world model. Now to actually control your agent, we have functions such as go to target, which is just saying, hey, for instance, the ball is in a particular position in the world. Go to target will ask you to start just walking towards the ball. Or it can be go to target relative. Relative means that we're specifying some offset from our current position in the world, which is, if it's relative, it's 0, 0, 0, the X, Y, and Z coordinates. And we're telling you a particular direction to walk in. And we'll also, if you want to turn in place, which is the second argument here, it will give you an angle to start turning. So these are just in this strategy file, things that you could comment out, or uncomment, I should say, and run, and you can kind of see how to generally control an agent. We have a number of these kind of demo behaviors here to just get a quick feel for, say, turning in place to face the ball. You can just stand still by returning skill stand. And also, of course, we have the ability to just call kick ball where you specify a particular type of kick. That can actually be kick dribble, where you're just walking through the ball and dribbling it. And we also then provide a second argument, which is the direction that you're trying to kick a ball. And with this particular base code release, we have a couple of kicks that you can also specify a kick forward, which is kind of a slower, longer kick, and kick IK, where IK stands for inverse kinematics, which is a faster but shorter kick. And I'll talk a little bit how these are defined in a bit. Currently, though, we have all that commented out, and to run the demo behavior that you saw, we just have this demo kicking circle behavior that I'm not going to dive into right now, but gives you an idea that you can kind of look through and get a feel for how we're actually coordinating the movement of our robots in the demo, asking them to move to different positions on the field, and even things such as collision avoidance, which we provide functions for that ask them when they're moving to different positions to try, for instance, walking around different objects like teammates or opponents and things like that. But really, if you want to, you can just only work in strategy.cc. Once again, specify where you want to beam in on the field at the beginning, and then based on information that you get about the world from the world model, decide what skill you want to execute at different points, and design your own team behaviors as such. So I'm going to briefly pause. If there are any questions about what I've been presenting so far, please let me know, and always happy to make this as interactive as people like. Feel free to ask questions, type, or if you want to, if I'm not noticing the chat, feel free to just unmute yourself and ask anything. Right. Now, I mentioned earlier that I've also, it's not pushed to GitHub yet, but probably will be, maybe even as early as today. Have just recently added a simple, what I'm calling simple soccer behavior that provides a team behavior for playing some very basic soccer, including formation control with dynamic role assignment, and it's just some very basic behavior. But unlike the kicking circle demo, we'll actually play soccer out of the box. So I'm going to show you what that looks like here. I guess I still have Roboviz up and running, and it is, let's see here. Yep, start simple soccer. Now, in this case, now we're having the robots beam onto the field in what is, instead of just a simple straight line, something that makes a little bit more sense, perhaps for playing soccer. And if you look at the code, these positions are just specified in the beam function, where I've added this sort of helper function that's we call get space for role. Each of the robots is assigned a different role position, say for instance defender or midfielder or forward, that specifies sort of a target base space position for it to be on the field. And the robots are assigned to these based on their uniform number, at least to start with the beam function. I'm going to start this actually running, and you'll see that in this simple behavior, the closest robot is always asked to just go to the ball and try and kick it towards the goal. And then we have robots, otherwise, if they're not the robot closest to the ball, are trying to assume different target formations on the field. And there's also some aspect of dynamic role assignment where they may switch off on different roles or positions where they may want to be on the field. Now, at this point, I'd like to mention something called RV draw, or the ability for agents to draw different debugging info, such as shapes, lines, points, objects, even text on the field that can help you debug things. Because right now I might be looking at this and saying, gee, I don't know what positions our robots are supposed to be, where are they planning to go, what are they thinking, what's going on with this uh, sort of greedy dynamic role assignment going on right now. So I'm going to show you what that looks like by turning on some code I have for that. This is documented in our code base. And in fact, the Bahia RT team, I think in their second tutorial at the beginning, talked a little bit of some more detail about some of the calls for this code for drawing things in Roboviz. So you might check that out. So I'm not going to go into a lot of detail. But basically, from your world model, you can call getRBSender, which is an object that allows for communication to Roboviz to draw different shapes, objects. And here we have one object for drawing a line, and as well as another for drawing a point on the screen. And in this case, we're going to be drawing a line from where our robot currently thinks it is for each robot to the target position in the formation that it has been assigned to and is planning to move to. And that actual position itself, which we're calling a roll space right now, we're also going to just draw a point on top of that. And we also will have a clear function here such that after every cycle, we'll clear out the drawings and draw new ones. Otherwise, we just have tons of drawings cluttering up our screen. So going to, now that I've uncommented those, put that in and run this again. And then you can get a better feel for debugging info, which will start to be drawn hopefully once the game starts, and get an idea for some of the ideas that you can use with this valuable debugging tool. So let's see if this works. Okay, so here you can see the robots. You can see kind of the target positions that each robot has been assigned to or asked to move to. And you can also get a feel for how well they're localized or where they think they are, based on if the start of the lines are actually kind of around the center of the robots. I should say these roll positions are currently just kind of hand-coded and defined as offset positions from the ball. So that's why if I move the ball, the robots just start quickly jumping around. You'll notice, though, that the robots aren't super efficient as far as this dynamic role assignment and switching off the positions that they're assigned to. And the reason is that this is just a simple encoded greedy role assignment function where certain role positions, actually those that are more defensive, are given higher priority such that they just quickly assign the robot closest to those positions. And so that will sometimes mean that robots that are have to walk a lot farther to get to other specific positions. This is not the most efficient thing. In the UTS Navilla code base, we use something called scalable collision avoiding role assignment, or SCRAM for short, which we've published on, that will allow your robots to quickly assume different formation positions faster than something like greedy role assignment here. But I'm not going to go into too much detail about that. But this is just an example, and I will, it's, today or this week, be uploading the code that shows exactly what I'm running here to get an idea for some of the debugging information that you can use in the code base. All right, so I'm going to close this down. Kill the server. And I also just want to quickly show, as I was talking about Roboviz and drawing here. In the meantime, though, I'm going to comment this code out so we're not drawing that again. Show you another use that's sort of hidden in our code release right now that may be of interest. If you were trying to, say, for instance, debug our localization code using our particle filter. And that is in the particle filter code. It's turned off by default, but if you were to change this flag from false to true, you'll turn on a lot of our debugging info that we've used for debugging localization and our particle filter. And I'll just show you what that looks like. Is that doesn't just clear the drawings at every second, but keeps around a history. So I'm going to start the server again, start up Roboviz, and start this simple soccer example again. And now each robot, so you can see as they're coming on the screen, is displaying a lot of debugging info about these little pink and blue dots are actually particles for the particle filter, basically randomly sampled position estimates of where the robots think they are. And they just persist on the screen so we can kind of gauge over time how the robots are moving, and kind of how our for instance our particle filter is actually working. So this kind of gives you an example of some more of the power of using the drawing code. I mean, the screen is getting pretty crazy here, but just as another example. And I believe, if I'm correct, I can clear all the drawings at any point I want, just using Roboviz once the screen gets a little bit too full, and kind of progress from there. But this is just another example of using Roboviz for debugging. Okay, I'm going to kill this off and also turn off that drawing code so that we're not always seeing all that craziness being drawn on the screen. Okay, so this is it was just some very high level basic. If you're just starting out, pointers to the code. The simple soccer will be added later, giving you this demo. But you can just look in strategy.cc right now, seeing these two functions of beam. Once again, that's just determining where you are jumping in on the field, as well as select skill, which is kind of your, once again, high level behavior of deciding what action each agent should be taking, such as walking to some target position, or kicking the ball, and I guess things like that. So now I want to transition a bit and dive into some of the other, I think, interesting parts of the code that are maybe a little bit more advanced, but that give you some more customizability, and things that you might want to really change and adapt for yourself to really improve the quality of your team's play, and be able to potentially field a more competitive team. Now, I've talked a bit about skills, so I'd now like to talk a little bit about how we actually define skills. And so, say for instance, when we ask to kick the ball, how does a robot know what motions to go through, or kind of a series of target poses to actually kick the ball? And that in our code base is going to be under the directory of skills. Yep, let me look here. Yep. So in our directory for skills, well, we have some basic C++ files for executing different skills. Ultimately, what they are doing is when we start the agent, loading in a skill file in what we call a skill description language that we parse. And this is what a skill file generally looks like. It's a series of frames that each frame is defined as a set of target joint positions, or a pose that the robot will move through. And in this skill description language, we have this is documented in the code base, but things such as set target joint angles, using, for instance, this set tar keyword here. And within that, we will specify different names of joint angles. For instance, this is the lower, or the left leg one joint vector. And then we will give it some target joint angle that we want our robot to move to. And you can either hand specify different joint angles, or you can also put in variable names for these, which I'll talk about in just a minute. These variable names are specified by parameters that you load in at runtime from parameter files for our agent, so that you can dynamically at runtime change how uh, the skills are doing things, change the joint angles or poses are moving through. And that's going to be particularly important for optimization and learning, which I'll talk about in a little bit here.
So I have a question.
Mhm.
So you're saying if I change values on the parameter files, the params files, they want to change real time on the simulator. I don't have to restart it.
Oh, it will change it at runtime. It will not change it in real time.
Oh, okay.
Yeah,
Okay, cool.
that's
When you
important.
compile. Okay.
Well, it will
When you
change it
start it.
at runtime. The compilation doesn't matter, and I'll get into that actually
Cool.
pretty much right now. So you can have these values hard coded in here, or as I said, you can have like named parameters. For instance, kick P3 could be like a value of 5 or something, saying, hey, we want to set the effector for lower leg 2 to be 12 plus 5, or whatever that value is defined as. Real quick, though, before I jump into parameter files, I also want to mention that we have some wait timeout before we move on to the next state or pose here. And you can use a wait command to decide how long before the agent then progresses to the next kind of target series of joint angles or pose as it moves through them. Now,
Cool. Sorry, with that wait function, do you guess the number, or like how do you know exactly how long it's going to take?
oh, so that's up to you to specify. For this file, it's hard coded. Actually, here's another one where I'm not sure if this one has it or not. For these values, you can also make them parameters and learn them. Initially, what we usually do for our skills is we hand code them, learn something that might be able to kick the ball a little bit of a distance, and then we'll take all these kind of hard-coded values, turn them into parameter names, and then as I'll show you in a little bit, use optimization and machine learning to learn better values for these that allow you to, say, kick the ball farther or walk faster or get up faster and things like that. So let me jump into what these parameter files actually look like. This is in the param files directory. We have a default set of parameters for all of our agents. These include parameters for affecting how our walk engine works. For instance, maximum step sizes and step heights and things like that, as well as values that I was just showing that are defined, with this dollar, variable name in our skill files. And so these files are loaded in at runtime. In our start scripts, you provide a path to a parameter file. Basically, just loads these in as a key value pair map. And then later, also at runtime, we load in specific skill files. And whenever there's some variable name in that skill file, it will then jump into the map that we've loaded for parameters and basically resolve the value for that variable by looking up its value in the map based on these parameter values that we have loaded in. I'll mention, though, that in these parameter files, it parses through them and sequentially. So say, for instance, if we have kick P1 defined here, later we can redefine that value later on in the file if we want to, or we can also load in multiple parameter files, and it will sequentially go through each parameter file when our agent starts up. And if it already has a value defined and it redefines that value, it will then just overwrite that value. And that's a way for us to, for instance, in optimization, generate candidate sets of parameters for different skills that we want to try out. Our robot will load in all its base parameters, then we'll load in a much shorter, smaller parameter file containing just parameters that we might want to be trying to learn at the moment. Those will, overwrite the existing default parameters, and then we'll be able to try those parameters out and see how they do on some optimization task, and I'll talk a little bit about that in just a minute. To maybe make this a little bit more clear, though, let me show you what our start scripts actually look like here. You can, I think, in our start scripts, specify with -pf or -params file parameter files that you might want to load in. Typically, we always load in default params.txt just to make sure that we have values for our all our variables and all our skills. If you ever were to load a skill file with some named variable that you don't have a parameter value defined for that, then the agent will just throw an assertion, give you an error message, and exit. But I should mention that in our start scripts, you can launch agents with different types. In the 3D simulation environment, we have currently 5 different robot model types, 0 through 4. And they vary with different, like some have longer legs. Type 4 actually has an extra joint for a toe and things like that. And when you're talking about kicking and walking, these different robot models, their body makeups, as they differ, the parameters that you'll want to use for them will change. They'll one with a longer leg will need to go through different target angle positions or series of poses to kick the ball versus one with shorter legs. And so for each of these different agent types, we also have a specific parameter file for that body type that we by default automatically load in. So for type 0, we also not only will we be loading in this default params.txt, but we'll be loading in default params underscore t0 in this case for type 0 for a type 0 agent, and then the same for all the other different types. So this is what happens when you start a team and run an agent. It's not only loading in kind of some base default parameters, but also parameter values are then used to overwrite some of those base defaults that are specific to that agent's body type. And then you can also additionally add in other parameters that you might want to change and mess with. So now I'd like to, though, as I've kind of given an idea of how we can define different skills and load in parameters for our skills, I want to talk about next a little bit of optimization and how we can use our code base with some hooks for actually learning skills. First, though, real briefly, I want to mention that it can be kind of hard to, if we're looking at our skill files, at least initially maybe coming up with some kicking behavior or something like that where you're typing in this kind of archaic format of just code of different series of poses and joint angles. It's kind of conceptually hard to think about of what the robot's going to do, as you maybe try and find just some very basic motion that can kick the ball a little bit that you might want to later learn or optimize. Now there is a third-party tool created by the AIUT 3D team. It was released, I guess, back in 2018 or so, or maybe even a little bit before that, that provides a bit of a, if I can pull this down here, GUI interface. And they have a paper on it that directly hooks into our base code release and allows you to kind of in real time change these values and see the agent assume different poses. This can be kind of a nice tool to allow you to create some initial behaviors for yourself or different poses and kind of see what's going on with that. That then will auto generate, I believe, skill files for you. I actually haven't used this myself, but I think it can be a very nice tool. And so if people are interested, I encourage you to check out this tool on GitHub. Okay, so next I'm going to talk a little bit about optimization. And if you were to go, not in their code base, sorry, in our code base, let me go up here to the optimization directory. We provide a little bit of a README and some basic information on running optimization tasks for our agent and how you can learn maybe a walk or a kick, which we provide some simple tasks for. So I want to jump in and show you what that looks like. Uh, so first I'm going to cd to our optimization directory here. And we have this script here, which is sample start optimization, which I'm going to just pull up here in VS Code. And this script, depending on if you've defined your task as being a kick or a walk, will run a special behavior for you, which is an extension of our normal now behavior class that will run a task of either kicking or walking in this case. And uh, during that task, the robot will be evaluating how well it's doing at that task, and you define what that evaluation might be. For kicking, it can be how far the robot was able to kick the ball, or for walking, how far it's able to walk. It will usually try this task several times, get some evaluation for each attempt at that task, and then write out to a file the average score or overall reward or fitness of how well it's done on that task. And this allows us, or at least UT Austin Villa team has used these types of agents to run algorithms such as CMAS, where a robot will run some evaluation task, try different parameters generated by some learning algorithm, continually iterate on that of trying new parameters, seeing how well they're doing, provide that feedback of how well it's doing to the learning algorithm, which then generates new parameter sets to try. And we, for instance, run many of these different learning or optimization tasks on a distributed computing cluster, but it's kind of up to people if they want to do machine learning to adapt it to their own resources. However, we give you some kind of basic learning tasks that you can do and show you a little bit of how you can have your agent actually control what's going on in the field and be able to craft these yourself. So I want to actually show you, though, what these look like and how to also set up the server so that you can run optimizations. So in this case, we're going to be running this sample start optimization.sh script here. And it takes in an agent body type. In this case, let's just go with 1 for now. It will also take in some parameter file that will contain parameters that you might be wanting to try out and evaluate. Once again, they'll just overwrite the current existing default parameters for the agent. In this case, I'm just going to pass in an empty file that I think I may have already created called temp/null, because I don't want to bother overwriting these for now. I just kind of want to see the optimization task run. And then we're also going to specify some output file, which is where the agent is going to write out how well it has done at that task. We're going to call out.text. Just as a side note, though, for our optimization scripts, they will immediately close as soon as they have detected the optimization is over, based on whether or not we've written this output file. And so if I already have one sitting there, before I run this, I need to first remove it in this case. And that's mentioned here. So I'm going to run this, but before I do, I also want to mention in this sample script that if you want to, normally this just runs like a headlessly. We don't see anything. It just quickly runs in the background. However, if you want, we provide a hook here that you can specify your path to Roboviz, such that will automatically launch Roboviz, and then you can see your task running live, so you can help debug it. So I'm going to start this running. I believe it's purposely going to fail, and then I'll show you why it's failed and what you need to do to get it to actually work in the with the server. Some parameter changes you need to make to the server. So we're going to run this. Roboviz is going to come up. Hopefully, we'll get an agent to come in here. Now, the agent is trying to beam in and kick the ball, and it normally would be trying to first check that it's beamed into the appropriate correct position, and then start kicking the ball. However, it is continually in this task failing the check for its position to know that it's in the appropriate position to start a kicking motion to evaluate it. And the reason for that is, and I'm going to kill this, and this is all mentioned in the documentation, for our optimization behaviors, which I'll jump into under optimization. For instance, our kicking behavior, we are accessing ground truth information from the server with this, for instance, this check beam function. And this is a feature you need to explicitly turn on in the server to get that information. Otherwise, it just comes in as 0 or a null value. So right now, our agent is asking or expecting ground truth information from the server when running optimizations. It's not getting that. So that's why it's just not doing anything right now. And we provide instructions for how to turn that on in the in our code base here. But I'm just going to quickly walk through how to do that. If we go to the server, I may have this already saved here. Some of the changes we need to make. Yeah. So this is your my server's installed in /user/local. And then this is a path to an RST file that you need to edit in your server if you want to run optimizations to turn on ground truth information. And you know, this is all mentioned here in the documentation, but basically we need to change these 3 values here to be true, so that the server gives us our ground truth position and orientation on the field, and also the ball, because we want to be very carefully evaluating exactly how far we're kicking the ball and things like that. We don't want noise in our own observations and things like that affecting our evaluation. We really want to know the true values. So that's why we need to turn these features on in the server. Only during go on, yeah?
Cool. Just wanted to ask, why are those values turned off?
Why did what?
Why are they turned off by default?
Oh, yeah, they're turned off by default for a number of reasons. One, when you're normally playing in a game, you don't want the server providing that information to the robots. That's not fair. You're not supposed to be getting ground truth information while playing a normal game. It's up to you to use localization, maybe particle filter, Kalman filter, some type of triangulation or something to figure out where you are on the field. That's information that you're not supposed to be able to have during a game. So that's one reason it's turned off by default. Another reason it's turned off by default is that many teams' agents don't even know about this information because it's turned off by default. If they get ground truth information coming in, they probably won't operate correctly. They'll fail to parse incoming messages from the server because by default, this information is turned off. Our agent knows about this feature and uses it, and so it can always parse it and it's fine with it. But if you were to, by default, turn this on and try playing games with many release binaries, you'll find that those release binaries would just immediately fail because they don't know how to deal with that information. And I also think when running through a proxy, I'm not sure the proxy will understand that either. I would say only turn this on when using optimization for our agent. In fact, what I typically do, I have 2 different versions of the server built. One that's has these flags, which I'm setting right now for machine learning and optimization, and another which just is your normal version of the server. And so that way you don't kind of confuse the 2 and try and run with these flags on with teams that won't support it. And you're, once again, not supposed to be getting this information during a normal game, but it's very useful for machine learning and optimization.
I have a question too, Patrick.
Mm-hmm.
But what would be the advantage when optimizing using this parameter set to true? I mean, what would be the difference if I optimize my agents using this like noiseless data instead of using a noise data? What would be the difference, you know?
Sure. Well, say for instance, in a kicking behavior, you may find that you fall over after kicking or you pitch forward or something like that. And that will add a lot of noise to where you think the ball is if you're trying to determine how far you've kicked it. And so you could accidentally, if you were using just your own observations, which have a lot of noise added in, say you end up learning a kicking motion that just causes you to kind of lurch forward or maybe fall over, making you think you've kicked the ball a lot farther than you really have. So you really want to know exactly what that information is. You want to know really exactly how well you're doing, and making sure that with ground truth information you're getting a very accurate, hopefully not very noisy evaluation, because having a good signal of how well a parameter set is doing for some particular skill is really better for being able to improve on that and learning. Does that answer your question?
I see. I see. I thought that that would affect the agent's performance, because during the game you won't have this noiseless data. So when I optimize it, if I optimize it without the noise, my agents will not learn how to deal with the noise. That's what I was thinking.
Yeah, then that's an excellent point. So here's the difference, though. We only use this ground truth information when evaluating the performance of the agent for machine learning purposes. When the agent's actually executing skills and doing things like that, we're still just using the normal observations coming in. Now, when I say that we're setting this ground truth information to be reported, that's coming in as an additional piece of information. The agent is still also getting all its normal observations, and it's just using that as normal. It's just that in these optimization tasks, we're then also taking this extra ground truth information provided and only using it not to control the agent, but using it for evaluation purposes of how well the agent may have performed on the task. So the real quick answer to that question is we usually don't use ground truth information to help the agent execute a task, just to evaluate it. Because yeah, as you mentioned, if you learn to do something well with ground truth information, then when that's gone, you may really struggle.
I think I understand what you mean. It's like the important thing is that the agent would know in a kick situation, for example, where he would want it, where the ball should be at. So without the noise, you would know where the ball should be placed when you make a good kick, when you make when you make a good kick, when you do that right. And when you put the noise in, it doesn't affect the performance in the game, but it does affect how the agent will learn that.
Yeah.
Is that right?
Yeah, I mean, really, we're just using the ground truth information for making sure that we've correctly initialized the optimization task, making sure that the agent is, starting in a correct position, and the ball is where we expect it to be, just starting out, and also to evaluate how far the ball has really traveled. But when the agent is actually executing the task as normal, it's using its normal noisy observations, so that it's not learned to rely in any of its own execution on ground truth information.
Okay, thank you, Patrick.
Mm-hmm. Yeah. So speaking of noise, though, another file that's helpful to change here, briefly. Let me see now, soccersim.rb. Because we want the agent to, when we beam the agent in to start an optimization task, we'd really like it to start in an exact position and make sure the task is initialized correctly. But by default, there is noise added to our beam commands. And so typically what we'll also do is turn off that noise, like this. And so now we don't have noise added in the creation of the task, and we also have the ability for the optimization behavior to really be able to directly learn or evaluate what's going on. So close that, and let's try running this again and see what happens. See if now the agent can really have that ground truth information. See, there's no jitter there. It just beams in directly, and it knows that it's in the right position to start the task based on the ground truth information. Now it has exact coordinates of ground truth information of the ball, such that it can evaluate how far it's kicked. It's going to run through a number of these tasks, but we have kind of printing out here. It's able to say, hey, the ball traveled exactly 6.53 meters. That is also equivalent to the fitness, which that's up to you how you want to actually evaluate a task. And the agent is just going to continually run through this. Not sure how many kicks we have it set to. Now, I'll also add, though, as the agent is doing all this, the agent actually is also connecting. This is kind of an important feature of our agent. It's not just connecting to the server, but during optimization tasks, it's also connecting to the monitor port. And the monitor port is where you can send training command parser commands. So the agent is actually able to move the ball around, set it. It can even move itself directly where it wants. It can pretty much change anything it wants about the world. It can also change the play mode and things like that. And allowing our agent that ability means that it can directly control, reset the optimization tasks, and do everything internally to itself. There are some teams, I believe, who may have some external framework that controls and adjusts things, but I think it's really convenient and nice to have that done inside the agent. So if your task might be dependent on some internal state of the agent, for instance, knowing that the agent is stable before making a kick and not feeling unbalanced, only the agent really knows that. And so the agent can then have that information and know when it's time to reset the task or actually start the task and things like that. Where if you don't have that direct information, you won't be able to initialize the task and set things as well. So I'm going to let this keep running in the background. It should finish up soon. But I want to just briefly look at some of the code that's going on here to give you a little bit better feel for some of how this works. Every task cycle, this is another important function in our agent, but really mainly only used during optimization. It's just a null op during normal gameplay for our behaviors, is this update fitness function. And this function can evaluate the state of the world, kind of see how things are going as far as your performance. If say, this is actually for walk task. Let me jump to the kick task here with its update fitness function. If you've completed 10 kicks, it will write out your overall evaluation to a file. It's also can change the play mode when we're ready to start a kick. And this is using this set mon message function, where this agent has a special flag when it started that says connect to the monitor port. And then it's able to, for instance, pass messages like this that will allow it to change the play mode. Let me just quickly search for some other examples of this. These tasks. It can change, for instance, the position of the ball. It can do a lot of different things, and you can check out the documentation in the server for the training command parser. But this is what allows the agent to really set everything up and control the execution of the tasks as it goes through them. This is, of course, though, something that you would not have normally during a game. If you were allowed to connect to the monitor port during a game, then you could just stand anywhere on the field and say, gee, I think I'd like to just ask the ball to be propelled towards the opponent's goal without even touching it. I mean, that would obviously be illegal. So this is just something that we can use during the course of play for optimization agents. And if you look in our start script, you will see that we have this --m port command where we're giving the agent the server port to connect to. And that's when that is option is given, which is not given during normal gameplay. That allows our agent to directly communicate to the server over the monitor port and control things. I mean, this is the same thing that Roboviz does. For instance, if you click around in Roboviz and move the ball, it's just sending training command parser commands that they're executing that on the server side. But our agent has the ability to also execute any of those, which is super useful for optimizations. Now, our task completed in the background and wrote out this output file, which in this case is just a single value of how well it did. That's to say, across in this case, 10 kicks it did, it had an average value of 6.503. That would be your overall kind of fitness, if you will. Now this task took a while, but there's no reason that in simulation we need to necessarily operate in real time. We can actually execute these tasks, very fast, and something like this maybe in 10 seconds if we can run much faster in real time. And so that's another thing that I highly suggest that one does when running these optimization tasks. And to do that, let me see here. This is once again in the base code documentation. You can go into the spark.rb file, and if we search for real time, am I getting the right file here? I have. Let me check that. It should be here in the documentation how to change this. Enable. Oh, it's not in that file. Sorry. It is. Let me jump back here. I'm gonna background that for a second. It is in RC Soccer. See here. Well, I will just change this. I believe it is in RC Soccer Sim.rb. Now let me check the path here. And I could, yeah, here it is. All right. If we go to this file, all right, we can turn off enabling real-time mode, and this will allow us to run things much faster. It's important though, if you're going to disable this, that you make sure in your spark.rb file, do you have agent sync mode turned on? Agent sync mode means that the server will wait for a sync message coming from each agent that it's connected to it before proceeding to the next simulation cycle. Because if you don't turn that on and the server is trying to run as fast as possible, and by not running in real-time mode, but once, just as fast as possible, it won't wait for responses from the agents, and the agent will just kind of flounder on the ground, not able to keep up with the speed of the server running. All right, but now that I have turned that on, now let's see what happens if we run an optimization. This is how you would normally, if you're not trying to debug it, what it would look like running. You see the server's running crazy fast right now because we're not in real-time mode. You see the agent is just very quickly executing this task over and over again. Instead of waiting a minute or two for 10 kicks, we're able to do it in a fraction of that time. And the agent is done. We can look at how well it did, looking at its output file. And so that's how normally you would really want to do optimizations, is to turn off real-time mode so you can run them really fast. Also just mention here, run this again. If you wanted to, you can, typically for machine learning, you'll be trying out different parameter files. I don't have any specific new parameter files to test, but instead I'm going to try, just to show a difference here, of loading in a default set of parameter files for a different body type, which should not work as well. Just gives you an idea of what would happen if you did try out different parameter sets. And instead of a kick that went 6.5 meters on average, or whatever that was, we'll probably see not as good, performance. See, using the wrong parameters, ones if we're trying out for a different robot model, I think this is for the type 4 toe model, you'll see that the robot does not do as well. And in fact, if we look at the output, it only kicked a little over an average of 1.5 meters. So lastly, just to show the other task here that we have, if you wanted to, you could, we have a switch statement in this, or a variable to switch task. You could also do a walk task. This is just for forward walking speed. And we'll try this. In this case, I think our robot's gonna beam in back here eventually, or not. Oh, oops, I think I broke something. Hold on here. Yeah. I've got too many Robovizes open. It's a problem. Let me try this one more time, and if see if this works. May or may not. Walk. I may have misconfigured something on this. The walk task isn't working right now. It was working earlier, but I'm not gonna worry about too much about it. Just show you that we'd have a robot here beaming in and walking as quickly as it can forward, and we'll quickly repeat that. I'm not sure what I may have accidentally changed in this file to break that, but anyway, that gives you an idea though of how you can run these simple optimization tasks. And you can kind of configure things, look at some of the examples to create your own. I mean, for our walking behavior, we will often have the agent not just walk forward, but learn parameters for walking and like an obstacle course and different interesting walking behaviors, because just walking straight forward is not necessarily the most useful thing, or you need to be able to do a lot more different kind of walking, changing directions things to do well when playing the game. So that anyway, this gives you an idea of kind of how to run optimization tasks, and you can look at the code in optimization behaviors, see how we're using this update fitness method to control, set up different optimization tasks, and also kind of evaluate performance of an agent to ultimately write out some overall kind of fitness reward for how well the agent's done. I should mention though that we do have some ongoing work for adding more of a RL gym type interface to our code base. So instead of just getting some overall performance metric or reward at the end of completing some task, you'll get some reward after every step in your task. I'm hoping that we can add something like that to our public code base release. Still a little bit of a work in progress, but we'll see. But that's really useful for deep reinforcement learning and aspects of that. But it's ongoing work that we're hoping to roll out soon, but I don't yet have a time frame for that. Okay, so before I move on though, I just want to quickly, oops, that's not what I meant to do, revert my changes so that we're not trying to run super fast.
So these changes that you made, they don't only affect the optimization file, right? They affect the whole game, right?
That's right. Yes.
Okay, cool.
Because they completely change the server. So what I usually do is, I think I mentioned, I have two different versions of the server installed in different locations. One that is just your normal vanilla server, and one that has all these changes in that I pretty much only run for optimizations. And so if you're doing something like that, if I jump back to the optimizations, I mean, you, instead of just running, RCS server 3D, I'll instead given, exact path to the executable of probably some version of the server that has ground truth enabled and is set to run not in real-time mode and things like that.
Nice. Okay.
Yeah. So let me kill this. And I just want to quickly reset something so that as I start running normally again, and because I don't have different versions of the server right now installed, that we're not confusing things. Hopefully I set things back up correctly. Let me make sure that I disabled ground truth again, because that will mess up stuff later if I'm not careful. That's not it. It's not neckhead. Yeah. So I'm gonna just quickly reset these. Okay. So I think this though is a really important, useful component of our agent. And if you really want to increase your competitive level of your team, you probably want to For instance, use optimizations like this to learn a longer kick. I mean, you can learn kicks up to 20 meters. You might want to also optimize some of the parameters for our walk engine to make it faster. Perhaps even for our get up behaviors. Really quick though, I want to just mention a little bit about our get up behaviors because they're not defined in normal skill files. Just as a quick side note here. So I close that. And I believe that is in behaviors. Have yeah, they're in our behaviors directory in something called check fall. And this is a function that we periodically call actually before we call select skill that decides if we may have fallen over. And if we have, then this sort of hard-coded function decides if we've fallen on our back or front, and then we'll start executing a series of motions to try and get up again. And rather than being explicitly defined the skill in a skill description language that we're parsing in, instead, we have sort of just hard-coded these frames in directly in the C++ code for how to have the robot get up. However, it still is parameterized with like parameters for the joint angles that you're using to get yourself up with things like get up params, names like this, that you will find in our params file. So you could also create your own optimization task where you purposely have the robot fall over and then see how fast you can get up. That's also something that we have done with our normal code base I mean, it's important once you've fallen over to quickly recover as fast as possible. You can also, another thing we've done is learn goalie diving behaviors. We don't have those included in here, but that's another optimization task that I think is useful that people might be interested in. We've kind of just given you some a very basic example of how to learn just a fast forward walk and a kicking skill, and it's up to you to consider how you might want to adapt that and learn whatever interesting skills you want. And you can define the skills through our skill description language and specify open parameters for them, which you then can use the some machine learning algorithm you want to try and learn good parameters for those skills. Okay, so a few other things I'd like to quickly touch on here. Something here, let's see. I also want to briefly talk about audio. And actually, instead of jumping right into the audio directory, I think a server com might be better. So in the server com directory, we have this file called primitives, which is basically taking our current joint angles and using a PID controller to determine what torques we want to apply to our joints to try and achieve those joint angles. And then it's ultimately calling compose action to generate a message to the server for what torques to apply to all of our different joint angles. But one other thing that it's doing is it is creating a message to communicate to our teammates using the say effector. And we provide sort of a base framework for doing that, something we released some years ago for a drop-in player challenges, maybe a common API or communication system. And it you can look in the audio.cc directory to see the underlying code. But basically, you can call make say message, and you allows you to communicate to your teammates by default the position of the ball, your own position, and if you've fallen over, you can add other aspects to it. But this is very useful because in the RoboCup 3D simulation environment, you have this kind of narrow view cone. You can't always see the ball, but if you don't see the ball, you can just hear what your teammates are saying as to where the ball is, and then immediately update your own world model as to where the location of that ball is. And so we provide this framework already integrated and hooked in, where we're able to make say messages here and in our parser code, which is I think in a parser directory. we'll parse these messages from our teammates and update our world model appropriately. So you can check out some of the code. I'm not going to go into it. It's a little bit complex. It uses ASCII 64 compression to ensure that we stay within 160 bytes, I think it is, which is the limit of the amount of data you're allowed to send in a message. And our communication system also accounts for the fact that only one agent from a team can communicate at a time every third simulation cycle. So it does kind of a round robin time slicing aspect where each team or each agent rotates through its time slot to communicate to its teammates information. So this is very useful. It kind of runs by default, giving you some basic information to keep your team coordinated. But for our base team, we add in a lot more information. For instance, we'll sometimes communicate positions of opponents to help our teammates update the world models for opponents are. We'll communicate when we're kicking a ball, the location that we're planning to kick the ball to, so that our teammates can kind of anticipate where the ball is going to go, and certain players can run onto that position. We'll also communicate things like role assignments to keep our agents coordinated with who should be going where. And one other kind of nice little feature we have is to help our agents out with their own self-localization. Maybe you got beamed for the sideline because you committed some bad foul, or you've fallen over and you get up and you just don't know where you are currently. You can actually communicate to say, I don't know where I am. And then the next teammate who sees you, and that teammate is localized, will then communicate to everyone, including you, your position. And so that allows you to just immediately quickly snap back into place for your own localization, having heard your position from a teammate to kind of, so you say, hey, I'm lost. And the teammate says, oh, you're right at that position. And then you're good to go again without having to wait a while for instance, the particle filter to converge. So that's a nice little feature of our code that's built in for communication. Just going to go through quickly some other aspects of these. So as I mentioned, in our audio directory, that's where kind of the underlying encoding and decoding of communication happens. You can look in that with some documentation if you want to modify that and add in your own things to communicate. Body model is a directory which includes a lot of the basic modeling and aspects and measurements for our robot, and some like inverse kinematics calculations and things. If your robot model is changing, then you might want to mess with that. Otherwise, you probably won't need to worry about that. Headers just defines a lot of important global values, such as dimensions of the field, names for hinge joints, and objects for in your world model that you might need to think about. So we go through these. IK-fast is really just some inverse kinematics calculation for some of our kicks. We do provide a Kalman filter, which I believe we're currently using to track the ball. One can also use those for localization. Libs directory, briefly mentioned this. This is where when you may be bringing in some third-party shared objects or libraries, you can just include them in this libs directory. And then by default, when we run a start script, we will update our load library paths to include this libs directory. And so this is important for competitions where you may have some binary that you've compiled and run on your own system where it can just find all its appropriate shared objects. But when you're now running on the competition system that doesn't have all those same libraries installed, instead you can just save off those shared objects, store them in your libs directory, and then at runtime, the agent will be able to load them in because the load library path will have been updated to that that libs directory. See here, math. Well, that's just some general math calculations, kind of some utility functions. I already talked a little bit about the optimization directory, which I went through for running some optimization tasks. The parser is, you probably don't need to change it unless something has changed in the server. And that's just dealing with processing the communication from the observations coming in from the server, and also works with updating or providing some information to your world model, which is down here. Your world model, once again, is generally just storing the positions of and kind of state of the world. Just a mapping of that. UT Walk is a module where we have our omnidirectional walk engine and kind of everything self-contained within there. You probably don't want to mess with this unless you're really trying to design your own walk or something similar to that. But by and large, you can probably consider this more or less a black box. So let's go through a few more of these. Particle filter, I briefly showed you a little bit of demo of what that was with the Roboviz drawing stuff. That's just for our local localization. RV draw, this is where you have all your functions that you can call for drawing different shapes, be it spheres, points, lines, as I showed a few examples of that for debugging. You can draw, for instance, text above your agent, change the color, sizes of things, decide when to clear them, when not to, even animate them, I believe. I'm not 100% sure about that, but that's what goes on in the RV draw folder. Scripts. These are actually just a few simple utility functions. As I mentioned before, that when you're preparing for a competition, you may be building stuff on your own system and loading in your own shared objects from libraries you've installed just on your local system that might not actually be on your or on the main competition system. And so we provide some quick scripts that will basically analyze your agent, which in this case by default it's called agent spark as your binary. Essentially, it's calling LDD on it, kind of looking at your shared objects, seeing where they're loaded, the past of them that have been resolved, and then just actually copies those into, I believe, your libs directory, so that if you were then copy that onto the system that is running a competition, you're set to go for that. So you can check those out. Those are just some simple utility scripts. Server com. I'm actually going to jump back to that in a minute, but I was briefly mentioning here earlier the primitives. That's once again where we're computing some of the specific torques that we want to send to or apply to our joint angles based on target joint angles that we want them to assume. And then we just set up a message to send to the server for that. Skills, once again, I've talked about that. If you click on it in our repo on GitHub, it's defining some of what the skill description language does, and so that you can create your own skills, and also some instructions for adding and loading them in, so the agent knows about them. And I also want to quickly talk about stats before I cover one other thing about the FAT proxy, which is a brand new thing. So stats, another kind of feature that we provide is this the ability to extend our normal now behavior with what we call a record stats behavior. And what it is doing is really just repurposing the update fitness function to record information about what's happening during a game, and then is able to write out all that information when a game ends. And we have scripts to activate this and record specific stats. By default, we're recording things such as the score of a game, maybe the average ball position, number of goals scored by different opponents. If bad things has happened, such as agents have crashed, you can even record things like if you want to modify what different types of fouls different teams have committed and things. And so this is something that the UT Austin Villa team uses a lot to just on our distributed computing cluster run hundreds or sometimes even thousands of games with this these scripts that adds this added flag to run this record stats behavior as an extension of our normal behavior. so that we have all this data accumulated, and then we can kind of run through this data and evaluate, how well we're doing, maybe things that we can look for improving. If we've made some change and we suddenly see that we're scoring a lot less, that's useful for debugging, particularly right maybe before we're going to submit a binary for a new round at a competition. We'll run a bunch of games with stats recording and then analyze them. So this is an internal behavior that you can run this script that will enable for our agent, and you can go into the record stats behavior file and add in your own custom stats if you want. And additionally, we provide a script that runs external to our agent. It's not a part of our agent, just a Python, or actually a shell script, I should say, that will connect to the monitor port of the server while a game is running and record stats that way. So this way you can just run any two teams you want. They don't need to be UT Austin Villa. They can be anyone, and we'll record whatever stats you want from that. Certainly things like score differential, if teams are crashing or other issues that might be happening. So this is something that usually after the end of a competition, I'll run 100, 1,000 games between every combination of teams, just kind of gauge their relative performance, and typically we'll publish this data as like a winning team paper or some other format, or just send it out to the league so that teams who don't have the capability or distributed computing clusters to collect this type of data can gauge that, but also for our own internal development, if you're using our code base, you can gather a lot of other state features that may be specific to our agent that you might want to monitor, such as how many passes did the agent complete, or things like that, or how many times did it try and shoot on goal and scored versus missed, which some external program wouldn't really be able to decide or figure out, because it doesn't have all that information that's needed from the internal agent. So I really quick though want to just show you what some of this can look like. So this is just some data I collected, I think, from the Offenburg tournament last year that was held, just taking release binaries and collecting lots of data from them, where the script automatically runs the opponents and then writes out when the game is over the statistics about them. You can kind of get an idea of what statistics might look at. This has some actual custom statistics for fouls, as well as the score and things like that. And then we also have written our own kind of Python summarization scripts that allow us to just quickly go through this data and report relevant statistics about the gameplay. So for instance, if we were to say, look at data from all the games between Bahia and Magma Offenburg, we see that there's an average goal difference of negative 4.8, meaning that Magma was winning by an average of 4.8. We can also, because we collected foul data on this, see how many times each team on average was committing different types of fouls. Looks like charging is pretty common. And we can even check for crashes and things like that. It looks like, Bahia crashed a few times while Magma did not in this case. So this is another kind of, I think, valuable analysis tool and scripts that we provide that people might find useful. Okay, so maybe the last thing though that I really wanted to cover is something I just added in yesterday, and it's the ability to work with the FAT proxy. This is this newly released proxy that the Magma Offenburg team has put out, in which an agent sends just a very high level dash or kind of walk commands and kick commands to this proxy. And the proxy will then run some of Magma Offenburg's own lower level code to translate those codes into how the Magma Offenburg's base set of walk skills should operate. And for kicking, it actually uses the training command parser to just propel the ball, as if you have just kicked the ball. This is, let me actually pull up the link to the proxy here. This is in Magma's GitHub repo. This is very similar kind of modeling commands that you see in the RoboCup 2D of dash and kick. So it allows teams to just really focus on high level behavior. and not have to worry about low aspects, and also provides a common platform where everyone is using sort of the same skill set, so you can directly compare a team's strategy, as opposed to a team with just lower level skills often doing better. So we're hoping to have some sort of side competition or challenge with that this year. And as I mentioned, though, I've now added some quick code to support that just very recently in our agent. So let me show you ideally what that looks like. I am going to just start up the server, start up Roboviz, and oh, actually I already have the proxy running, but I'm going to close it and restart it. And so what the proxy does is it you specify some new port for your agent to communicate on, and the proxy takes the messages from the agent and then communicates it its own kind of commands to control your agent, then sends directly to the normal server port 3100. But if we were to now do start fat proxy, you check that. Yep. You can see what this looks like. There is if I run this, you'll see you have to specify the port that you are communicating with on the fat proxy. I just put it as 3110. And let's see if this actually works. Yep. So we're loading up our team. This looks like just our normal base behavior as normal, but you'll see in a second here when we start this running with this kind of normal base kick circle behavior, instead of using UT Austin Villa skills, we now actually look a lot like the Magma Offenburg team. We were just directly translating without even having to think about it, just as a thin layer, all of our own behaviors for walking and things like that, and kicking to the API needed for the fat proxy. So the agents, when they're walking around using the controlled walk engine of the Magma Offenburg team, and when they're kicking, they're actually having commands set to the training command parser that propels the ball forward, as opposed to actually needing to, make contact and kick to the ball. But this script just adds a fat proxy flag, I believe, that's passed to the agent that just pretty much automatically enables this. I'll give you one more example of this. If I pull up that script, which is this start fat proxy, if I wanted to run that simple soccer demo, which I'll be, should be pushing out shortly to the code base, which I think we can enable with this simple soccer option. We'll have that same kind of demo behavior running with start fat proxy. Oh, get the port right. See if this runs. Yeah. So once again, we just in the simple soccer case, just with adding this flag, we have beamed right in onto the field. But instead of executing the UT Austin Villa walk skills and kicks, instead we're going to be using the exact same behavior, but now using the low-level behaviors provided by the fat proxy, including the kick skills that just kind of automatically propel the ball forward. An agent just says, "Hey, kick," and then the fat proxy calls the training command parser to push things forward. So this is for teams who are interested in competing in this challenge. This is a very accessible, easy way to do it. You could technically even just run with this fat proxy flag, I believe, and not even have to worry about changing any other low-line skills, or I should say strategy. It's going to use different low-level skills, and it will just kind of work and do something, but you probably want to tune it or think how with this set of skills, how your strategy might change. I should also add, is I just added this yesterday. This is not particularly tuned, so there's probably some needed work to be done on this. And I also want to mention, though, is just kind of a pointer to the code that is by and large doing this. If we were to search for in our code base to see what changes were made for this. The fat proxy flag. If you look at code that is around this, you can see ways that we have modified and changed the code to support the fat proxy. In particular, in our primitives file for sending out the specific dash and kit commands. So for teams who want to quickly support this in their own code base and they're not using our base code, and particularly if you're using C++, but maybe even Java, this can give you an idea, sort of a template for how you might be able to take some of your own code and create the commands that will work with the fat proxy. So I'm really hoping that teams will be able to easily adapt as we have a kind of a template for doing that and work with the fat proxy this year. I think it's kind of an exciting a new challenge that we'll be supporting, and hopefully this will enable many teams to participate in that. So that, I think, is a lot of the main things I want to cover. Let's see here. I'm going to kill something. I also want to quickly go over just some of the command line arguments that we have for our start scripts and agent. Just shut that down. If you want to see some of the commands we have for our agent, which by default, the binary is called agent spark, you can run just help. And in this case, the commands are host, which by default, this is the host of the server. It defaults to localhost, so you don't have to specify it. If you want, you can also specify a port, which defaults to 3100 if you don't. Type is the agent body type for an agent. You can load in a custom model for an agent if you want to, which is through an RSG file. If you want to change the team name, instead of using the default value, you pass in --team. You set your uniform number of your agent through unum. You pass in different parameter files through this params file argument, as I mentioned before, and then just a path to these parameter files to load them. And you can have multiple of them in sequence, and later ones will just override previously defined parameter values. We also provide some base behavior or kind of stubs for a penalty kick goalie and penalty kick shooter behavior. If you add these arguments, and we also have start scripts for this that automatically include them, they'll run these behaviors, which are just extensions of our base now behavior. And those are something that also, if you're going to compete, you should just fill in the kind of beam position and select skill for having a goalie and penalty kick shooter. Gazebo, which I'm not going to go into, if you want to run the 3D simulation plugin for Gazebo. Optimize just is a flag we use for specifying different optimization agents, which I talked about the example kick and walk ones, which you can create your own new behaviors and have them be loaded or initialized in the agent through this optimization flag. Record stats, that's running that record stats behavior kind of on top of the now behaviors, which I mentioned for recording relevant information about goals scored or penalties and things like that. Monitor host is something you probably won't need to ever use unless you're running Roboviz on one machine and your agent on another machine and you want to use drawing commands. By default, this is just localhost, but if you want to send drawing commands to an instance of Roboviz, which is running on a host different from your agent, you can actually do that by also specifying the host of the monitor. And then monitor port, which by default, we don't, if you don't specify this, you don't connect to the monitor port of the server. This allows you to, which we use in optimization agents, to connect to the training command parser so that we can reset states of the world, move balls around and things like that. And then you also have, which I just added, this fat proxy option, which will take your low-level commands and add in or process them to commands that are accepted by the fat proxy. Actually, I shouldn't say process your low-level commands, process your high-level commands, like where you want to walk where you want to kick the ball, we'll process that as a message being sent to the FAT proxy, which in turn will send the appropriate control commands to the server. And now the other thing to look at is the basic arguments for our start scripts. Not too many to worry about here. If you need to specify a different port than the default one, you can do -p. If you need to specify a host the server's running on, especially if it's not localhost, you can just type that. You don't even need an identifier for that command. If there isn't one, it just assumes that it is the host. And this next one here is actually quite useful. Just show you briefly what that is, but that's for specifying a team name. So for instance, if you want to run the two versions of the team against itself, you could do something like, so you make sure that I don't have the proxy running here. Actually, I don't think I do. Okay, you can start just a normal team as so, and it will load in with the default team name, in this case, UT Austin Villa Base. Now, if you want to start a second team, though, you can't use that same team name, or it'll try and load it on the same side and things won't work. You just simply add the T argument and add in like a test for another name of a team, and it will then change the name of that team, and you can quickly load in a different team. And even if it's really the same binary team, and then they can kind of play against each other. This will probably be not so great as they're just mirroring each other, but that's a quick way of doing that. You don't need to edit the start scripts or anything like that. See if there's anything else I wanted to mention here. Looking at the help. You can also specify, just as you can with a single agent, the monitor host, if you want a team to draw things to a version of Roboviz that's running on a different host. And you can also change the parameter files or add additional ones that are going to be run on every member of the team, this -pf or --params file argument to your start script. So that just gives you some quick helpful commands for running and things with our start scripts and our agent. And now just as kind of a recap of sort of some of the code flow, as I went through a lot of things, but just kind of to step back and give sort of a general overall picture now that hopefully you have some idea of some of the different components of what happens to the agent and what's going on. So I have this sort of simple blocked out diagram of some of the pieces of the code, highlighting important functions I think that you might want to work with, and just to abstract away a lot of the other stuff, things to focus on. So when you start our agent, by default, you'll start an instance of the now behavior class, or you might have extended it if you're running like an optimization agent or a penalty kick behavior or something like that. Initially, in the main function, we'll be calling load params, which will just go through all your parameter files, load in the different parameters into a map. And then in the, I believe, constructor of now behavior, it will call read skills from file. In this case, what it is doing is reading in these different skills in the skill description file I mentioned. And for any place that you might have a variable name in there, it will look to resolve that value from the already loaded in parameter values in the params map. Then we start in our basic execution and just a continuous loop until the agent is killed or ended. And at the very top level, we have this think method that we continually call and loop on. And within think, one of the first things it does is it has a parser and calls parse. So that's just getting all the information from the server and also using that to populate the world model. Then it will always, every cycle, also call update fitness. Update fitness is just a null up. It's not used for normal behaviors for games, but for things like optimization agents. That's where it's kind of evaluating the state of the world to maybe think how well an agent's doing at some task, or if it's recording stats, what, if a goal has been scored or a foul has occurred. And also typically here, when we're running optimization task, we'll be running setmon message or something like that to control the state of the world, to reset or set up different optimization tasks. And then finally, we call act. And act, we'll call the important functions. So the main two I've mentioned before that you really will always need to focus on, and maybe can almost exclusively focus on if you're just starting out and looking to create a basic behavior. And that's the beam function, which when it's time at the beginning of a kickoff, where you specify where to beam, and then select skill, which specifies a particular skill to take, which you can infer from the current state of the world. Now, I'll mention though that select skill is not necessarily called every simulation step. Some skills, like a kick, will occur over multiple simulation steps. And so select skill won't be called and will be blocked from being called until a skill finishes executing for those that are temporarily extended or occur over multiple simulation cycles, which kicks usually do. For walking, we can usually just kind of update every cycle, so they won't block. But things like goalie dives will also block typically if it's just kind of this series of motions that you're going through. And if we're executing a get up behavior, that will actually be triggered and identified before we call select skill, and will automatically be executed and will block things until the agent is in a prepared and standing motion. And then once we have a current skill that we're executing, and we have target join angles or control signals for that that we want to have, we're calling compose action, where we're computing all the different individual torques and the message format, as well as communication we might want to send to teammates. That gets made in compose action, and as a final message sent out to the server as we act in the world. You also want to check out world model, particularly when you're in the select skill method, which has some very basic functions for getting your own position, your angle where the ball is. You can also ask where any world object is, such as your teammates and opponents, and it provides all of that. I mentioned that we do have a drawing module with Roboviz that's useful for debugging. Some particularly useful functions are things like drawing points and lines and just clearing all the drawings. If you want to mess with communication, you should look at the process here message and make say message for processing, a message that a teammate might have said, and also creating your own message to communicate stuff. And then for skills, checking fall is where we operate on how to get up if we've fallen, and also identify if we've fallen, which we use accelerometer measurements to decide that. But some really important skills that you'll see in the demo behavior in the strategy.cc file are just going to general target positions on the field. If you want to just have the agent do specific things like turn in place or walk forward or backwards, you can call get walk. And then kickball executes actions for kicking the ball. And in fact, a lot of the kicking code, if you ever want to fine tune that or mess with that, will I think I may have forgotten to mention, but is in behaviors in kicking.cc, I believe. So that is kind of a whirlwind tour of our agent. I meant to create a slide for this, but didn't. Of things so that you as a new team or a team already using our code base might want to do to really improve performance. And so some things like that would be to learn or optimize better skills. That's a great way to really help yourself out. You want to look in at strategy and formations and kind of think about how to implement that yourself. And while I will be pushing out this simple soccer thing shortly to the code base, that's still just a very rudimentary example of how to do formation control and role assignment and things like that. But that's I think the other big area of focus. And those would be two of the biggest things, things to improve performance. Anyway, that's kind of all the main things I think I wanted to talk about today. So we're right around 2 hours now. If there are any questions people have, feel free to ask them. I'm happy to revisit or dive into any topics or answer any questions you might have. And also, I should say, you know, if you have questions later, you can always you know, follow up and reach me at my UT Austin email address right here. And you can also see links to some of the papers explaining a lot of what we've done. We've pretty much published everything that we're doing, even if we haven't released it in code. And I should also, I think it's very important to mention that and highlight that there have been a lot of contributors over the years that are listed on the code base that have really made this possible, you know, over the past gosh, 10, I think even plus years of development. So really want to highlight the important contributions of the other authors of this code base. Okay, so with that, I think I'll stop talking for a bit. If there are any questions that people have, please let me know. Either I guess in the chat, although I don't have that up right now, or just feel free to unmute yourself and ask questions. I can't find the chat right now. Hold on. Windows. For whatever reason, if there is anything in the chat, I'm not seeing it because my chat window isn't open. I'm struggling to find it. If anyone has, can let me know if anything's in the chat just by saying so. Please let me know. Here. Oh, here we are. Chat. Not seeing anything right now. Okay. All right. Well, if there aren't any questions, probably looking to wrapping this up now. This is being recorded. Hopefully it recorded correctly. And in the following day or so, we're looking to post this maybe on YouTube, maybe as a link on the current 3D Sim repository, and or potentially probably a link off the tutorial page here. All right, well, thank you everyone for your time. I hope you found this valuable, and I also look forward to seeing some of you hopefully participating in this year's RoboCup 2021 competition. So thank you. I'm going to try and end this now. Yeah.